Hi students, welcome to lesson 3.1, Graphing and Evaluating Piecewise Functions. I should probably warn you right up front that I'm sitting right now making this video with my dogs in my lap, and one of them is going after a bone, so you'll hear that in the background. She's chewing away at it, so I apologize in advance. So in the lesson today, we are going to be looking at graphing and evaluating piecewise functions. Let's find out right away, what is a piecewise function? So a piecewise function is a function that is made up of two or more functions, each with their own unique domain or inputs. So sometimes we'll have real life situations that they change over time, and one single rule or equation or function cannot describe the situation over all different intervals of time. And so when that occurs, a piecewise function can allow for that change that might occur over time. So each of the pieces of the piecewise function describes how the situation is behaving at that point in time. We'll look at some of those real-life situations later in the lesson, but to start off, we're going to take a look at how to evaluate a piecewise function. So to evaluate any piecewise function for a specific x value, we're going to find the piece or part listed that contains the domain value or the x value and plug it into the corresponding rule. So each x value will only correspond to an interval of one specific part of that function. So in other words, whatever the input might be, that input will direct us to the piece of the function that we want to utilize. So let's go ahead and take a look at evaluating some piecewise functions. So here's a piecewise function, and this piecewise function has a piece of the function that is quadratic, see here, and this is how this particular situation behaves for x values that are less than 2. So basically these, the way that the format of a piecewise function works is this. You've got this interval here, and this helps you to decide when does the function change behavior. And this says it changes behavior at -2. So when x is less than -2, it behaves like x squared minus 1. And then after that, so when it gets to -2 and beyond, it actually instead behaves like a linear function, 5x plus 3. So say I wanted to evaluate f of -5. So -5 is the x value, that's the input, and so if I were to take that -5 and figure out which interval it is in, it would actually lie in this interval right here, and so it would say use that first part of the function. And that means what I'm going to do is substitute that -5 into the part x squared minus 1. So I'll put -5 in, I'll square it and subtract 1, and that'll give me the value of f of -5. So f of -5 would be -5 squared, which is positive 25, minus 1, and that's 24. Now if I wanted to find f of -2, so this time -2, it's actually right on the boundary between these two. So it's a little bit tricky which one you use, and so you have to look at, well, is -2 less than -2, or is it greater than or equal to -2? And of course it's equal to -2, so I would have to use the second piece of the function, and so I'm going to go ahead and substitute -2 in for x in that second piece of the function, and I'm going to find the value. So that means f of -2 would be 5 times -2, which is -10, plus 3, and that's -7. Let's go ahead and make part C a you-try question. So we're going to see what f of 7 is. I'm going to pause the video. You can pause the video, excuse me, and try to find out what f of 7 is. Okay, so I hope you were able to try that and successfully found that f of 7 was in fact 38. So this next piecewise function is much more elaborate. It actually has 3 different pieces, and so of course it has 3 different intervals, and each of the parts is a little bit different. This first piece of the function is a linear function, 1/2 x plus 3, and that's the function. That's the way the function behaves for input values that are less than or equal to -4. If instead x is greater than -4 but less than 1, then it's going to behave like the second function, -x minus 1. And finally, if we have input values that are 1 or higher, so in other words, when x is greater than or equal to 1, it's going to behave like this, 2x cubed plus 9. So we'll try a couple of these together, and then we'll leave C for you tries, just like on the last example. So g of 2. So first thing you have to do is take a look and see which part of the function 2 belongs in that interval. And so the 2 belongs in the interval right here because 2 is greater than or equal to 1. And so I'm going to substitute it into this function right here, 2x cubed plus 9. When I do my substitutions, I always want to put parentheses around whatever my input is. So I'm inputting 2 in. So I'm going to take 2 and cube it, and 2 cubed is 8. Then 8 times 2 is 16, and 16 plus 9 is 25. Let's try one more. So g of -1. So g of -1 would actually lie in this interval right here because it's between -4 and 1. And so that means I'm going to substitute into the -x minus 1 function. So again, I'm using parentheses, so when I substitute my -1 in, and then it says take the opposite of it and then subtract 1, the opposite of -1 is 1, and then minus 1 is 0. So g of -1 is 0. So go ahead and pause the video, and let's try C as a you-try question. Pause the video now. And so that one also turned out to be 0. So g of -6 is 0. Let's go ahead and turn the page, and we're going to take a look at some of the graphs of piecewise functions. So there's lots of different strategies that people use to graph piecewise functions. But in general, you graph a piecewise function by graphing each piece of the function over the specific interval stated for the domain. So basically what this is saying here is I'm going to have 2 parts of the graph. One of them is going to be how the situation behaves before and when I get to -3. In other words, when x is less than or equal to -3. And then it's going to change over and it's going to behave differently past -3. And so usually what I do is right away when I see that break point in the interval, which is at -3, I go right down to the graph, and at -3, when x is -3, I actually put a vertical line to kind of just divide up the graph into these 2 pieces, and on one side it's going to behave like the first piece of the function, which is f of x equals x, and then on the other side it's going to behave like this, -2x plus 1. Now, as you get more comfortable with graphing piecewise functions, you may use a little bit simpler strategy to do this, but for the first couple, we're going to take a look at using a table, and because this graph, is in 2 pieces, we're not going to use the entire table for the first piece of the graph or for the second piece. We're going to actually split it up and use half of the table for the first piece of the graph and the other for the second part. So notice this table has a column for x values, so we have that, right? And usually we have an x and a y column, but since we have 2 different outputs, we're going to use the first column for the part that's the first piece, which is x. Okay, so in other words, f of x equals x. We're going to graph that one there, and then the other one would be -2x plus 1. And so like our outputs basically are going to be found by putting them in each of these pieces of the function. Now if the input is -5, I'm actually going to come up here and of course use this piece right here because it says that's true for when x is less than or equal to 3. I wouldn't put it in the other one. And in fact, I wouldn't put a -3 in there either. So what I do is where that breakpoint is, where that graph changes over at -3, I'll take my table, and usually I do a better job of trying to balance the table. I usually try to put x values a few before this breakpoint and a few after. This table is kind of set up not ideally, but it still gives us an opportunity to plug a couple points in. And so then what I do is the first function, I'll plug in the values up to that breakpoint, and then after, I don't bother to fill them in, so I'll just kind of scribble out the rest of that table for this one, because I know I'm not going to plug in things like -1. I'm not going to plug in 0 or things like that, because they're outside of the interval for this function. Now the other one, I'm not going to plug in until I get to -3. And I guess technically I really shouldn't plug in -3, but I'll show you why once we get this graph drawn. If we don't plug in at this breakpoint into both pieces of the function, we're going to have a gap in our graph. So what I do is I just will cross off the table before we get to the breakpoint for the second one, because I know we're not going to really start plugging in until we technically get past -3. But I also want to plug in -3. And when I do, though, I'm going to put an open dot on it. So remember how we talk about how open dots, they're kind of associated with that just greater than or just less than? And so we can do that on this graph, too. So we'll go ahead and plug in that breakpoint into both functions. But when we actually graph those points for the second function, we'll use an open dot. There you go. Let's plug some of these in. So if I plug -5 into x, then my output would be -5. So basically what it's saying is whatever the input is, that's also what the output's going to be. If I plugged in -3, I would get -3. I'm going to go over here and plot those points on the graph. So at -5, my output is -5. So I have that ordered pair -5, -5. So let's see. -5, 1, 2, 3, 4, 5. There's a point right there. And then -3, -3, right there. I could have put in things before -5, like -10 or -5,000 or whatever. And so that graph is actually going to continue to the left. Like I could keep putting in smaller and smaller x values. So if I were to make this piece of the graph, I would extend it all the way to the left forever. But to the right, it's only going to continue up until it breaks over to the other piece of the graph at -3. And so I stop right here at this boundary line, and I use a solid dot because in this top interval you can see it says or equal to. Now I'm going to start using the other piece of the function, the -2x plus 1. So if I plug -3 into -2x plus 1, that's -2 times -3, which is 6 plus 1, that's 7. If I plug in -1, that's -2 times -1, that's 2, plus 1 is 3. Plug in 0, I'll get 1. If I plug in 1, that's -2 plus 1, which is -1. And finally, if I plugged in 3, I get -5. So now I'm going to go on the other side of the graph, of that boundary line, and I'm going to graph this other piece. I'm going to graph the point at -3, 7, which is right here. But notice I used an open dot because technically that point doesn't exist there. This graph doesn't actually start until just past that boundary line. So then the next point, -1, 3, 0, 1, 1, -1, 3, -5. And I could continue to put in larger and larger x values, but this graph is aligned, so all I really need to do is connect these points. And it's going to continue on to the right forever. So now that graph actually is a function. It does pass the vertical line test because even though it looks like there's 2 points on the same vertical line there on that boundary line at -3, one is an open dot and one is a filled dot. So technically that open dot doesn't count as a point on that line. It's just shows that it comes right up to starts just after that boundary line at -3. Now the table is not necessary. It really is just for your use. So if you choose to use the table, that's fine to organize your points. And if you don't, that's fine as well. But this is probably the best strategy that I've seen when you're first starting out, is to make that table just to kind of get that process down. So let's try another one. Now this piecewise function changes behavior at -1. So at -1, I'm going to put this vertical line down. That just kind of gives me kind of this imaginary breakpoint in the graph. And I know that on the left-hand side over here, it's going to behave like that piece of the graph, -3x minus 7. And to the right of that line, it's going to behave like this, which is g of x is equal to -5. And that just means that that piece of the graph is going to be a horizontal segment because there is no variable. It's like saying y equals -5. 0, -5, 1, -5, 2, -5, and so on. That's just going to be a horizontal segment that's going to go out to the right forever. So again, this graph is a function because it does pass the vertical line test. The only place really in question would be right there at that boundary line at x equals -1, but because 1 dot is an open dot, and that's for that first piece of the function, and then the second one has the fill dot on it, it technically does pass the vertical line test even there. So this is a function. It's just that part of the function behaves like a negatively sloped line, a slope of -3 in fact, and whereas the second piece of the graph is a constant function. So let's go ahead and turn the page and we'll do one more of the graphs together, and I'll leave you one for you try. Probably the best one for us to do together is number 6. So we'll go down to this one at the bottom and we'll leave the one at the top for you try. Because this one at the bottom has 3 intervals. So that makes it a little trickier, and of course then the table is more complicated. So let's do that one together. So this time, because I have 3 intervals, I'm actually going to have 2 different breakpoints. This graph's going to break at -2, because you can see here, there's that break at -2. There's also going to be this break at 4. So I'm going to go ahead and put 2 vertical lines, one at -2 and one at +4. So here's the one at -2. This is going to be the first place it changes behavior. And then the one at 4. So with our table, we're going to have 3 columns, one for each piece. So that first column is going to match up x, the input, with the output of 2 times x. The next one with -1 minus x. And then a third with this constant function, -3. So basically we want to kind of look at this as if it were like 2 problems like we've just done. So maybe look at the first 2 columns and treat it like it's a, it's, say maybe just look at these 2. And then after that you can look at the next 2 and do exactly what we did with those last ones. So taking a look at those first 2, we're going to have a change in behavior at -2. So on this table, I know that right here is where we're going to see that change in behavior at -2. And so that for that first part of the function, 2x, I'm only going to substitute in values -2 and before. And after that, I'm going to just scribble out the rest of that table. I'm not going to bother plugging in things like 0, 1, 2, 3, 4, and so on because they're really outside of the interval. It says this function only exists when x is less than or equal to -2. So I'm going to plug in -4. I could plug in -3, -2. I could plug in things less than -4. But I get a pretty good sampling of points if I just plug in -4 and -2 since it's a line. So plugging in -4 would give me an output of -8 because -4 times 2 is -8. Substituting in -2 would give me -4. And now I have the points that I need to graph this. I know that it's going to be to the left of -2. I'm going to plot these 2 points, one at -4 and one at -4, -8, and one at -2, -4. And when I connect these, I just know that it is going to only go to the left of this boundary, and it will go on like that forever. Now the second piece, I know I'm not going to substitute values in that are before -2, and I'm also not going to plug in any values past 4 because it says it's only true between -2 and 4. So after 4, I'm going to go ahead and scribble that out. I'm only going to substitute in values between -2 and 4. And it is a line, so I maybe don't really need to substitute in for every one of those. So if I substituted in -2, I just know that when I do that, I'm going to put an open dot on that one because, again, this one has a less than sign, so it's saying technically -2 is not in the interval, but if I don't want to have a big gap or a hole in my graph, I'm going to substitute in -2 and draw an open dot there, and then just say this graph starts exactly right after that when x is a little bit bigger than -2. So substituting in -2 there would give me -1 minus -2, which would make a +1. Substituting in a 0 for x would give me -1. Substituting in 1 for x would give me -1 minus 1, that's -2. Substituting in 2 would give me -3. Plugging 3 in would give me -4, and 4 in would give me -5. Now on this one, I'm also going to have an open dot because it says that it's less than 4. So technically I shouldn't have plugged in 4, but I want the graph to go right up to that line and just shy of it. So on both of those spots, I'm going to put an open dot. So here is those points plotted. And I'm going to connect those between those 2 boundary lines. Now that final piece starts here at 4. So there's a little bit of an overlap here. I mean, technically one line comes right up to the boundary line and the other one begins afterwards. So this one, where the function says f of x equals -3, I never would have filled anything in until I actually get to 4 on this. So it's like this piece of the table I don't use at all, and I don't start plugging in until I get to 4. And again, even then I can't really substitute values in because that's a constant function. So basically what it says is no matter what the input is, the output's going to be -3. And so plotting those points would look like this. 4, -3, 6, -3, 5, -3, whatever. Every single one of them is going to be an output of -3. And I'm going to have this horizontal line right there that will go out forever to the right because, again, at that point, it exists for everything greater than or equal to 4. So let's go ahead and take a look back at example 5 and just give you a chance to test your skills with a U-try. So real quick with this question, I see that either the table or the interval is going to have to be changed if we're going to use the table to graph it. So let's go ahead and just change this interval here to say that the change in interval happens at 1. Actually, you know what? Let's do this. Let's change it to -1. So these are going to be for x is less than -1. And actually, let's change one of these to say or equal to. So let's go ahead and change this to the first one to be x is less than -1 and the second interval to be x is greater than or equal to -1. Let's go ahead and pause the video and give this one a try as a U-try question. Tune back in to check your work. All right, so thanks for giving that one a try. Take a second and check through your table and look at your graph. And if you have any questions about how that turned out, be sure to take a note and bring that up when I see you in class. let's go ahead and take a look at a real-life problem that might be modeled by a piecewise function. Let's turn the page. So this is sort of the quintessential kind of piecewise function example to start with. This is a pretty common real-life situation that comes up where one function cannot be used to describe a situation over the entire possible domain. So Shelley earns $8 an hour for the first 40 hours that she works. Okay, so that's typical. 40 hours is considered full-time work. If you work 40 hours or under, you get this set rate, $8 an hour. But she earns $12 an hour for each hour over 40 that she works, which is actually called time and a half. And if you think about, if you take $8 and you multiply it by 1.5, that gives you $12. So that's time and a half wages, $12 would be. And that's typically what happens when you work over full time is, let's say you made $10 an hour normally. Well, then time and a half would be $15. Or if you made 20, your time and a half would be $30 an hour instead. So basically then any number of hours past 40, you just get paid a larger per hour salary for it. So this asks me to sketch a graph of Shelley's earnings versus the number of hours that she worked up to 60 hours, and then write a piecewise function for the graph. So actually we're going to write the function first, and then we're going to graph it. And so this table, we're just going to kind of organize our information. So for hours worked and the pay, so if she works on, let's say we call hours H, less than or equal to 40, she's going to get paid $8 per hour. And if she goes over 40 hours, she's going to get paid $12 an hour. So basically this part right here, the hours work, is going to become our interval, this piece over here where it helps us to kind of split up this function into the two pieces. And so I know that for when H is less than or equal to 40, I'm going to have to write a function that says she gets paid $8 an hour, and that when H is greater than 40, it's going to have to take into account this higher wage for the additional hours that she works. So the first part of the function, this part where she's just working 40 hours or under, that's easy. That's just $8 times the number of hours that Shelley works. So that part of the function is pretty straightforward. Now the second part's a little more involved, because if we get to this second part of the function, so if she gets to where she's working over 40 hours, she's actually already earned 40 hours worth of $8 per hour pay. So in other words, she's made $8 times 40 hours, which is $320. And again, that comes from taking $8 an hour and multiplying it by 40 hours. But now Shelley is going to get paid $12 an hour. But if I just put 12H, then that would imply that she's getting paid $12 for every single hour. And that would be drastically overpaying Shelley, because she's already made $320 at $8 and for the $8 an hour for 40 hours. But now we're saying we're going to pay $12 an hour, but it's really not $12 an hour. It's $12 an hour for every hour past 40, and this is how we can say that: $12 times H minus 40. So why we have to use H minus 40 is because we have to take into account that if we're at this part of the function, we've gone past 40 hours, and those 40 hours have already been paid for right here, right? This has already been taken into account that the first 40 are paid at $8 an hour. So what this is going to take care of is right here. This is just the additional hours that she's getting the $12 at. So that would really make sense if you think about, let's say Shelley worked 42 hours. So I would be jumping down here to use this part of the function, and I know if I plugged 41 in there, or 42, excuse me, in there, that would work, because that would say 42 minus 40, which would give me 2, and that means I'm getting paid 2 hours at $12, and then this $320 represents the first 40 hours of pay, which I will have already earned if I'm at that second piece of the function, because that means I'm past my full-time hours of 40 hours. So here's my piecewise function, including my interval. And if I wanted to graph, so this is my piecewise function. And if I wanted to graph this, it's going to change over to a new interval at 40 hours. So this first part of the graph, I could just graph by picking some different number of hours to work. So if Shelley worked 0 hours, then she'd get paid $0. But if she worked 20 hours, 20 times $8 is $160. So that would be maybe like right in here. And then if she worked, say, 30 hours, 30 times 8 would be 240. So there'd be 30 hours and 240, maybe right here. And so on all the way up to the 40 hours at $320. And that would be right here at the boundary. After that, it's going to jump up and be a little steeper. And so then if I say I plugged in 50 hours. So if she worked 50 hours, she'd get 50 minus 40, or 10 hours paid at the $12. So that would be $120 plus 320. So let's see, this would look like that. That would be $440 for 50 hours. At 60 hours, it would be $560. And we could even see if she worked 41 hours, what that would be. So at 41 hours, that would be 342. So that's back over here just past 40. So that would just be barely past this line right there. And so essentially what's going to happen is this graph's going to take over after 40 hours, and it's just going to be a little bit steeper line. And that's because the slope of this line is now $12 an hour for that piece of the graph. So we're going to go ahead and end the lesson here, and we'll save this final example for us to do together when we're in class. So that gives us an opportunity at least to have gone through one where we evaluate a piecewise function, actually a few where we graphed them, and now a real life example. So we'll pick up when we see each other in class, and we'll go over some more examples. See you then.